Hi everyone, welcome back to my channel. Today we are going to learn about multi-hop retrieval. So there are some problems that single retrieval can't solve. If we have some complex query like I want to cancel my account, what happens to my wallet balance and my premium gold status? So this query cuts across three different domains or documents. One is account cancellation. Next one is the wallet balance, and next is the membership detail. So how are we going to fetch all of the relevant information or chunks with just one call, one retrieval? Because certainly all of them cannot be retrieved, and hit rate would definitely go down because neither of these documents would be fetched properly. So this is a problem just one call for retrieval wouldn't solve. So when we are trying to do query, neither of the account management file would be fetched nor the premium membership file would be fetched. So in total, our hit rate would be 0% because neither of these two documents exist in a single document inside the corpus. So even if we do re-ranking and try to get the chunk to a higher position, that wouldn't work in this case. That's why we are going to use something known as multi-hop retrieval, where we are going to retrieve multiple documents. How are you going to do that? For what kind of queries? Let's understand. Let's understand the type of multi-hop queries. First can be inference based. So we have to deduce something from indirect evidence from different documents. Say what refund policy applies to my account for a certain years. So we are going to understand, we are going to research about refund policy pertaining to that particular year. Next would be comparison kind of queries where we have to extract and reason across multiple entities. Say we're comparing different kinds of membership. And third would be temporal based. So something where we have to establish a chronological order across the time indexed resources. Say I change my wallet, what is the policy, how am I going to forfeit it? So that we have to follow something called as query decomposition, where we are going to identify different sub-questions in the given query. And for each sub-questions, we are going to run independent retrievals. Then we are going to merge, do re-ranking, and then we are going to do give that as context to the LLM via context assembly. So if I have a complex query, I'm going to break it down into smaller sub-questions. Say I have sub-question one being what happened to the wallet balance after deletion. So that will fetch from account management and wallet related documents. Next one is another sub-question is what happens to premium gold status on deletion. That time we are going to fetch it from premium membership document. So right now the hit rate that was 0 initially because no right document was fetched. Now it can suddenly increase to 100% because all relevant documents are fetched now. We can also use the concept of parent-child retrieval. And this also helps us in having a lighter fix. Say if we are fetching a document or a chunk and some of the information does not always fall inside the limitations of a chunk, it has to go outside the chunk as well. Say a short sentence that also explains about wallet balance is outside the chunk that is the most relevant chunk. So what can we do is we can always fetch chunk index 1, -1 and +1. So the chunk before the particular relevant chunk and chunk that comes after whatever relevant chunk we have, that ensures that we don't have to do a second retrieval call. We can get most of the relevant information in that particular chunk, set of chunks. So it's lighter and cheaper than multi-hop. This can be used to solve the multi-hop problem first, and then we can escalate it to decomposition of the query and having multiple retrievals. Since we're doing multiple retrievals, it's going to impact on the cost as well. So it's going to be expensive. Last step would be to do context window engineering. That is how we are going to arrange all the chunks present from our retrieval and from the top k chunks, how we are arranging it and presenting it to the LLM. So first we have to drop certain redundant or overlapping content. If we are fetching something that is relevant, we would have some overlapping if we have enabled overlapping and chunking, or say something like that. And then we have to promote the high signal chunks or the top chunks to the top positions. That is when we are doing re-ranking. We're going to do that. And then finally, we're going to assemble all the context and then present it to the LLM. So something that has more weight or more importance would be placed first. Something that's redundant would be dropped. So context assembly is the last mile between correct retrieval and correct generation. So we are going to present something that is cleaner and understandable to the LLM so that the LLM understands it better and does not make the same mistakes. We are reducing the noise. So like we learned in the previous videos, whatever we present in top of the context or say in the end of the context has more weightage than something that is present somewhere in between. Say some context that is in position 1 or line 1 has higher chances of LLM considering it seriously than some relevant chunk being somewhere in between the context window. So that's what we're going to ensure. So whatever is important is placed early in the context. So that's about context window engineering. Thank you so much for watching my channel. Keep supporting. Bye.